Download this code from codegive.com, link in the description below. Mastering Java 8 streams, a deep dive and pitfalls to avoid. Java 8 introduced streams, a powerful feature for processing collections of data in a declarative and efficient manner. Streams allow you to express complex data transformations and computations in a concise and readable style. However, the elegance of streams can sometimes obscure potential pitfalls that can lead to unexpected behavior, performance issues, or even incorrect results. This tutorial provides a comprehensive guide to mastering Java 8 streams, covering core concepts, common operations, and, most importantly, highlighting and explaining those critical pitfalls to avoid. 1. Understanding the core concepts of Java 8 streams. At its heart, a stream represents a sequence of elements that can be processed through a series of operations. The key characteristics of streams are: not a data structure. A stream is not a data structure like a list or set. It's a computation pipeline that operates on data from a source, example a collection, an array, or an I/O channel. Laziness. Stream operations are generally lazy, meaning they're executed only when a terminal operation is invoked. This allows for efficient processing because intermediate operations are combined and executed as a single pass. Immutability. Stream operations don't modify the underlying data source. They create new streams with the transformed data. Consumable. A stream can be consumed only once. After a terminal operation is executed, the stream is closed, and you can't reuse it. If you try to reuse a consumed stream, you'll encounter an illegal state exception. Internal iteration. Streams use internal iteration, which means the iteration process is managed by the stream API itself, freeing you from manually looping through the data. This allows for better optimization by the underlying implementation, potentially leveraging parallelism. 2. Creating streams. You can create streams from various sources. From collections. From arrays. Using stream.of. Using stream.generate, and stream.iterate, from I/O resources. 3. Stream operations, intermediate and terminal. Stream operations are divided into two categories. Intermediate operations. These operations transform the stream and return a new stream. They are lazy and are chained together to form a pipeline. Examples include: filter, predicate keeps elements that satisfy the predicate, a Boolean valued function. Map, function T, R mapper, transforms each element from type T to type R using the mapper function. Flat map, function T, stream R mapper, transforms each element to a stream and then flattens the resulting streams into a single stream. Useful for transforming nested collections. Distinct, removes duplicate elements based on equals method. Sorted, sorts the elements in the stream, naturally ordered or using a comparator. Peek, consumer T action, performs an action on each element as it's processed, primarily for debugging or side effects. Limit, long max size, limits the stream to the first max size elements. Skip, long n, skips the first n elements. Terminal operations. These operations trigger the execution of the stream pipeline and produce a result or a side effect. After a terminal operation is performed, the stream is considered consumed and cannot be reused. Examples include: for each, consumer T action, applies the action to each element in the stream. To array, collects the elements into an array. Asterisk collect, collector T, A, R collector, accumulates elements into a collection or other data structure using a collector. This is the most versatile terminal operation. Asterisk reduce, binary operator T accumulator, reduces the elements to a single value using the accumulator function. Asterisk count, returns the number of elements in the stream. Asterisk any match, predicate T predicate, returns true if any element matches the predicate. Asterisk all match, predicate T predicate, returns true if all elements match the predicate. Asterisk none match, predicate T predicate, returns true if no elements match the predicate. Asterisk find first, returns an optional T containing the first element, or an empty optional if the stream is empty. Asterisk find any, returns an optional T containing any element, can be non-deterministic in parallel streams, or an empty optional if the stream is empty. Asterisk min, comparator T comparator, returns an optional T containing the minimum element based on the comparator. Asterisk max, comparator T comparator, returns an optional T containing the maximum element based on the comparator. 4. Common stream operations with examples. 5. Common pitfalls to avoid. This section highlights the most common pitfalls developers encounter when working with Java 8 streams and provides solutions for avoiding them. Asterisk pitfall 1, reusing consumed streams. As mentioned earlier, a stream can only be consumed once. Attempting to perform a terminal operation on an already consumed stream will throw an illegal state exception. Solution * create a new stream instance for each terminal operation. If you need to perform multiple operations on the same data, create a new stream each time. If you're performing many operations, consider collecting the data into a list or set and then using that collection for subsequent streams. Pitfall 2, side effects in stream operations. Streams are designed for functional programming, which emphasizes immutability and avoiding side effects. Using side effects within stream operations, especially within for each, peek, map, and filter, can lead to unpredictable behavior, especially when using parallel streams. Side effects involve modifying external state outside the stream pipeline. In the example above, the for each operation adds elements to the process enums list. This is a side effect because it modifies a mutable external state. In a parallel stream, the order in which elements are added to the list becomes non-deterministic, leading to potentially incorrect results. Solution * avoid side effects in stream operations. Instead of modifying external state, use terminal operations like collect to accumulate the results into a new collection. If you absolutely must use a side effect, example for debugging, be aware of the potential consequences, especially with parallel streams. Pitfall 3, misusing optional values. Optional is used to represent values that may or may not be present. Common stream operations like find first, find any, min, and max return optional values. Not handling optional values correctly can lead to no such element exception if you try to access the value when it's empty. Solution * always check if an optional value is present before accessing it using isPresent. Use or else, default value, to provide a default value if the optional is empty, or else get, dash, to compute a default value lazily. Consider using or else throw, dash new my exception, to throw a custom exception if the value is absent and that situation indicates an error. Pitfall 4, unnecessary boxing/unboxing. When working with primitive types, example int, double, long, using stream integer, stream double, or stream long involves auto-boxing, converting primitives to their wrapper classes, and unboxing, converting wrapper classes back to primitives. This can introduce performance overhead, especially when processing large data sets. Solution * use specialized stream interfaces for primitive types, int stream, long stream, and double stream. These interfaces provide methods optimized for primitive types, avoiding unnecessary boxing and unboxing. Pitfall 5, incorrectly handling flat map. Flat map is a powerful operation that transforms each element of a stream into a stream and then flattens the resulting streams into a single stream. A common mistake is to return a single element instead of a stream from the mapping function, leading to incorrect results or runtime errors. Solution * ensure that the mapping function passed to flat map returns a stream or a type that can be converted to a stream, example using collection stream. Pitfall 6, performance issues with parallel streams. While parallel streams can significantly improve performance for CPU-bound tasks, they're not a silver bullet. Using parallel streams inappropriately can actually decrease performance due to the overhead of thread management, context switching, and combining results. Parallel streams are most effective when the data source is easily splittable, example ArrayList, arrays. The operations are computationally intensive. The data volume is large enough to justify the parallel processing overhead. The operations are stateless, do not rely on shared mutable state. The order of elements is not important, or you can sort the results later. Solution * carefully evaluate whether parallel streams are appropriate for your specific use case. Benchmark both sequential and parallel streams to determine which provides better performance. Consider the cost of splitting, merging, and thread management when deciding whether to use parallel streams. Pitfall 7, reliance on ordering in parallel streams when it's not guaranteed. Parallel streams can execute operations in an unpredictable order. Therefore, relying on the order of elements in a parallel stream can lead to incorrect results, especially when using operations like for each, find first, and mutable reductions with collect. Solution * avoid relying on the order of elements in parallel streams unless it's explicitly guaranteed, example using for readable. Use stateless operations and avoid mutable reductions that depend on order. If ordering is critical, consider sorting the results after the parallel processing is complete, or use a sequential stream. Pitfall 8, mutable reduction without proper synchronization. Mutable reduction involves accumulating elements into a mutable container, example a string builder, ArrayList, or custom object, using the collect operation. When using mutable reduction with parallel streams, you need to ensure proper synchronization to avoid race conditions. Solution * use the 3-argument version of collect, supplier A supplier, by consumer A, T accumulator, by consumer A combiner. The supplier creates a new mutable container for each thread. The accumulator adds an element to the container. The combiner merges the containers from different threads. Alternatively, consider using collectors methods like joining, or toList, which handle synchronization internally. Pitfall 9, confusing map and flat map. It's easy to confuse map and flat map, especially when dealing with nested data structures. Map transforms each element of a stream into another element, while flat map transforms each element into a stream and then flattens the resulting streams into a single stream. Solution * understand the fundamental difference between map and flat map. Use map when you want to transform each element into a single new element. Use flat map when you want to transform each element into a stream of elements and combine all those streams into a single stream. visualize how the data is transformed at each step. Pitfall 10, inefficiently using peak. Peak is primarily intended for debugging and side effects, example logging, during stream processing. It should not be used for performing core transformations or operations that affect the result of the stream. While peak can modify the state of an object in the stream, if that object is mutable, this is generally not recommended due to the potential for side effects and unexpected behavior, especially in parallel streams. Solution * use peak primarily for debugging or side effects, such as logging. Avoid modifying the stream's data or performing essential transformations within peak. Use map, filter, or other intermediate operations for data transformation. 6. Best practices for using Java 8 streams. Favor functional programming. Strive for immutability and avoid side effects within stream operations. Use specialized streams for primitives. Use int stream, long stream, and double stream to avoid boxing/unboxing overhead. Consider parallel streams carefully. Benchmark and analyze the performance impact of parallel streams before using them. Handle optional values correctly. Always check if an optional value is present before accessing it. Use collect for accumulation. Use collect to accumulate results into new collections or data structures. Leverage method references. Use method references to make your code more concise and readable, example string to uppercase, integer sum. Understand stream pipeline execution. Be aware of the lazy evaluation of stream operations and how terminal operations trigger execution. Avoid premature optimization. Focus on writing clear and correct code first. Optimize only when necessary based on profiling and performance measurements. 7. Conclusion. Java 8 streams provide a powerful and elegant way to process collections of data. By understanding the core concepts, mastering common operations, and avoiding the pitfalls outlined in this tutorial, you can effectively leverage streams to write concise, efficient, and maintainable code. Remember to prioritize functional programming principles, carefully consider the performance implications of parallel streams, and always handle optional values correctly to fully unlock the potential of Java 8 streams. Good luck streaming.